Okay, welcome back again, everybody, to our statistics class notes. We're now on page 118, and we're in section 8.1 where we're talking about hypothesis testing in general, and we've talked about how to form the null and the alternative hypotheses. Now we're talking about how to form the test statistic that we're going to use to compare our hypotheses to see which one is likely to be true or not. So, the test statistic that we want to form is a z-score. So it's the observed value, which is p hat, the sample proportion, minus the null value, what we're assuming to be true about the population, which is p naught, divided by the standard error. So that's a typical form of a z-score, right? The what you got from your sample minus the mean divided by the standard deviation. So that's a typical form of a z-score. Now, but we're going to use the standard error now, where we're going to use p naught, because that's what we're assuming to be true about the population. So we're assuming the standard error then using that same p naught. So it's p naught times 1 minus p naught divided by n, and then take the square root. Again, p hat is the sample proportion from the sample data, and p naught is the proportion that's hypothesized in the null hypothesis, which was p equals p naught. Okay, so let's calculate the test statistic for our global warming example. So remember what we assumed to be true back in 2000. This is our sample here of 2015. We reported that 55% of Americans. So that was our assumption of truth, the null, right? P equals 0.55. So this is our p naught. So that means plugging that into our standard error first, because we need that for the z-score. Plugging that into our standard error, we get 0.55 times 1 minus 0.5 divided by 1,000, the sample size. That equals 0.0157. So the test statistic now, which is a z-score, but we start to call it the test statistic for our hypothesis test, is p hat, which was 68%, so 0.68, minus p naught, which is the hypothesized, the null hypothesis value, which is 0.55. Divided by the standard error of 0.0157. So I get 8.28. And I'm like, holy cow, a z-score of 8.28. That means our 68%, what we got from our sample, is 8.28 standard deviations above the 55% that's hypothesized in the null hypothesis. So the observed value, p hat, 0.68, is 8.28 standard errors above the null value, which was 0.55. This is so far above the null value that we will conclude the null value is very likely not true anymore. Okay, now we got to be kind of rigorous about how we're going to make that conclusion, though. We have to have a cutoff point. And the way we're going to do that is to look at something called p-value. P-value will be a way we measure our surprise. So when I first read this, z equals 8.2, I'm like, holy cow, 8.28 standard errors above what we thought was the mean. It's not likely we would have got that 68% if 55 was really the mean. That's kind of what my thought process was, but now we need to be a little bit more rigorous on how we measure that. So we're going to use p-value. So the null hypothesis tells us what to expect when we look at our data. If we see something unexpected, that is, when we are surprised, then we should doubt the null hypothesis. If we're really surprised, like we just saw up here in this part F, we should reject the null hypothesis altogether. So the p-value gives us a way to numerically measure our surprise. It reports the probability that if the null hypothesis is true, our test statistic will have a value as extreme as or more extreme than the value we actually observed. So that's what p-value is. So in other words, if we get a p-value close to 0, that means we are really surprised. And the way the p-value would be is the probability that z is 8.28 or more, so greater than or equal to 8.28. Of course, that's going to be really close to 0. Large p-values, which are close to 1, means we're not surprised at all, and there's not enough information to reject the null hypothesis. Now, the last thing we got to choose is significance level, and we actually choose the significance level. That's the probability of making the mistake of rejecting the null hypothesis when, in fact, the null hypothesis is true. We want this to be low. Right? Think about that court of law type situation, innocent till proven guilty. So we're trying to prove something is guilty. We want to have a lot of proof. We want this probability of making the mistake of saying they're guilty when in fact they're really not guilty is low. So this symbol for the significance level is alpha. We read that as this guy, alpha. This is the Greek letter A, which is called alpha. For most applications, a significance level of alpha equals 0.05, so we're going to take about a 5% chance of being wrong. That means again, if we're outside that 2 standard deviations, outside of 95%, we'd be in that 5% range. But sometimes we want to be even more sure, like we want an alpha of 0.01. Or sometimes even we're okay with being less sure, an alpha of 0.10. Okay, so we'll start to put this all together soon, just a second on the next page.